the bright orange dye which we get. Okay, now let's have a look at the second pair. The second pair, what I see is I have an acid chloride and I have a ketone. That's a ketone. I'm just opening the display formula for you. And that's the acyl chloride. I'm just trying to open the formula there. And that's the Cl on the side chain. Okay, so chemical test to distinguish between them. Well, easy test would be, don't forget that's the ketone there. And if it's a ketone, you could react this with 2,4-DNP. So that gives you an orange color there, no reaction there. So that's not a ketone, it's an acid chloride. It will not react with 2,4-DNP. So that's one test. You could also carry out another test using silver nitrate. Reason why silver nitrate? Because it's very easy for acyl chlorides to release the Cl out as a Cl minus. It undergoes hydrolysis with water in room temperature, so it very quickly releases the Cl as Cl minus. And if you add silver nitrate, it gives you the typical white color, white precipitate. So that's how you confirm this one. This will not release the Cl minus very easily. Don't forget, for it to lose the Cl, you need heat. So it needs a much higher activation energy. Very easy for acyl chlorides to release the Cl minus. So the second test could be a silver nitrate test, what you could do. There's a third test what you should consider. You could work with iodine dissolved in sodium hydroxide. This particular chemical test has been shifted now from A level syllabus to AS level syllabus in 2016. It's basically called as an iodoform reaction test. This is very good test, especially when you have CH3C double bond O in any of the compound. So because we have CH3C double bond O, you get a very unique yellow precipitate CHI3, which is the iodoform, the triiodoform, as one of your product, apart from the other oxidized product. It's a mild oxidizing agent. It works if you have CH3CO or CH3CHOH in any of the compound. So yellow solid there, no reaction here. So three tests recommended: silver nitrate, the iodine plus NaOH test, or you could go for the, as I said earlier, the 2,4-DNP. So we have three tests to distinguish between these two. Okay, let's have a look at the last pair here. The last pair what we have is an aldehyde propanil against propanone. That's very straightforward. Again, coming from your AS level syllabus. So you shouldn't think of 2,4-DNP because don't forget aldehyde and ketone both will react with it. But you could think of tolerance region and you could think of Felling's region. You could even think of acidified dichromate. Tolerance region will react with this to form a silver mirror. It can oxidize aldehyde. This one will not show any reaction, so that's an easy test. You could think of Felling solution. Felling solution will give you the brick red precipitate with aldehyde, no reaction there. You could even think with acidified dichromate, which is orange in color, oxidizes aldehyde to carboxylic acid, orange color changes to green, no reaction there. So you have a couple of tests there to work with: the acidified dichromate, the tolerance region, and the Felling's regions. Any of these can be used. All of them positive for aldehyde and negative for ketone. Okay, let's have a look at the C part of the question. There's some information given in the question. It says E plus F is supposed to give you some polymer, and you should quickly look at the structure of polymer and look at the link present in it. You see there's an ester link there. The moment you spot the ester link or the amide link, if you look at the first question, it says what type of polymerization made this polymer. The answer always has to be condensation. So anytime you see an ester link or amide link, the polymerization is condensation polymerization. So that's the answer of C part 1. Now in C part 2, the question says draw the structures of the two monomers E and F. Now to try to figure out the monomers, the trick is you need to cut the polymer in such a way so you get some information about the monomer. So obviously you need to cut the ester link, but then where to cut the ester link? Now you must cut the ester link here after the CO. So here after the CO. When you hydrolyze the ester, you cut it after the O, but when you want to spot the monomers, the trick is to cut after the CO, because what happens is this bit here that you notice, CO, can come from COCl or COOH. So this could come from carboxylic acid or the acyl chloride. This bit here, the O, has to come from OH. So that makes your job very easy. So I see one monomer here. So I have that's my benzene ring. So just have a OH here and an OH here. So that takes care of that. And then I have this bit here, 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5 CO. So I could put a Cl. Don't forget, I can even put OH there. It could be a carboxylic acid, could be an acyl chloride. Both answers are correct. Now for the third question, it says suggest the conditions needed to make the polymer G from E and F in your lab. Now it depends on what you selected as answers in E and F. So let's say this was E, and let's say 1, 2, 3, 4, 5. Let's say this was let's say this is E and this is F. You have different situation that might happen. The first thing you have to do is you have to make sure that phenol, this is OH on the ring is phenol, it is dissolved in NaOH, and you react this with this. So when you react these two together, the Cl of this will go and the H of this will go, and you get that. So if you have these as your answers, it's much easier. You just have to write one line. So dissolving E in NaOH and then reacting this with F, and that's how we get this polymer. But suppose you have selected this as your answer in the previous question. Let's say you have OH as your one of the monomers. Now you need to make some changes. So the first thing you have to do is to convert this into COCl. So the carboxylic must be changed into COCl, and you could react this F with SOCl2, you could react with PCl3, or you could react with PCl5, any of these. So once you do the reaction, so your answer should say react F with, if this is your F, react F with any of these three, so that you change this to this, and once you have done, then react this substance with E dissolved in NaOH. Don't forget, phenol is much more soluble in NaOH because NaOH is a much stronger base compared to H2O. So always the solvent here is NaOH all the time. So it depends on what your answer was. So if your answer was OH, don't forget, change the OH into Cl by reacting with this, and then take that compound and react with E dissolved in NaOH. So there could be two ways of writing this answer. Now, if you look at the fourth part, it says one of the monomer, E or F, could be changed to make a more rigid polymer, which will have similar chemical properties as compared to G. So which could be that monomer, and what would be the new structure that you would suggest? Now what we could do is, we could work with this one. 1, 2, 3, 4, 5. We could work with this monomer. It's much easier for us to understand this one, because what you see here is a long CH2 hydrocarbon chain. So if you have long chain, they will probably coil within each other, and that brings about some elasticity. If you want to make this more rigid, the concept would be to cut short this chain, make it smaller. That means instead of taking 5 carbons, I can make it just 2 carbons. I can reduce this chain. So I could reorient it this way. It could be just this, CH3, CH2, CH2, or just even 1 carbon. So the idea is reduce the carbon chain from 5 carbon to 2 carbons or 3 carbons, or 4 carbons, anything less than this, that should be fine. So this is a possible answer there. So this is CH3, CH2, COCl. That's the 5 carbon. If you notice, this is 1, 2, 3, 4, 5. This is 5 carbon, this is 3 carbon. So you got chain is reduced by 2 carbons. So this makes it more rigid. You could even think of this answer, CH3COCl, where it's only 2 carbons. Smaller the carbon chain, more rigid the polymer. Well, this question, let's have a look at question number 7 now. And in case you're wondering why I jumped to question 7, that's because question 6 has been removed from the syllabus as for 2016 specifications. Now question 7 talks about NMR. Now in NMR we talk about the proton NMR, not the carbon-13 NMR. The question says what two factors could influence the energy required for this promotion. It talks about the factors influencing the constant flipping of the high energy and low energy state with respect to magnetic Liouville forces of the proton, which could be alongside or opposite to that of the external magnetic field. Now, a couple of factors responsible for it. One, the strength of the external magnetic field. So if the external magnetic field has got a higher strength, the split of the delta E, the difference of energy gap between the low and the high energy state, is going to be much higher. So that's one. Second, the kind of chemical environment the proton will find itself. So if it depends on, does it have an electronegative element, does it have non-electronegative element, is there shielding, de-shielding, so all that depends on the chemical environment. So two factors, chemical environment of the proton and the strength of the external magnetic field. Now let's have a look at question number B part, where there's an NMR spectrum mentioned, and I'll just draw the main essential peaks for you. Now first off, the number that you see on the top of the peak is the number of H atoms, the number of protons that you're looking at, and now 9 protons are resonating in an identical environment, and the only way you could figure this out is to think of 3 CH3s. So if you have a carbon connected to 3 CH3s, and that's why you're getting a singlet here, which means all 9 of them are adjacent to a carbon who doesn't have any H, and you see that carbon has got no H. It's following the n+1 rule. So this is the bit who is giving you this peak. Now there's a molecular formula mentioned as C4H10O. If you add up all the atoms here, this is already 4 carbons done, and it has 9 H's done already. So that leaves you with 1 H and 1 oxygen. So you really don't have, there's no need for you to have a look at the data booklet. You know there is 1 H and 1 O, and that obviously is the one here. You must be careful about the peak of the H of the OH. It has a huge range in the new specifications, from 0.5 to 5.0 chemical shift. And the only way you can really be sure of that is by doing what is called as a D2O shake to figure out is it the H of the OH peak or not. But as of now, for this particular question, all you could do is, once you have worked this one out, you only were left with H and O, so it has to be the OH there. That's how. So you try to piece that information and put it together there. So the actual structure of the compound becomes this. It's always a good idea to clearly state the chemical shift values underneath the protons. So this one has given a peak at chemical shift somewhere around 2.0, and this is the one somewhere around chemical shift 1.2. That's the structure of the compound. Now the second part of the question says there are 3 other isomers of this compound J that you got in the previous page, and it must contain the same functional group as J. That's the alcohol group. Good to know this is tertiary alcohol though. Draw the structure of 2 of these 3 isomers and indicate how many different chemical shifts do you think they will show in the NMR spectrum. So this question is a challenge for isomerism for you. So you could work out isomerism under AS concepts, and let's have a look at the labeling of different hydrogens. So I can have 4, that's CH2OH. That could be one structure. So I'm sure you know the labeling of hydrogen. So that's A, B, C, D, and E. So which means it will have 5 peaks. And we could think of, for example, CH3, CH3, CH2OH. So that's A, B, C, and both the CH3s are connected to that carbon, so the environment of all the 6 protons here are same, so that's going to be my D, which means this will have 4 peaks. So four peaks shown by this one, 5 peaks shown by this one. Well, that's it, students. That's all. The remaining question which is there has also been removed from the syllabus, so I'm going to end my video here. So I hope you are satisfied with the video. I hope you enjoyed it. Go through it and revise your concepts once again. I'm going to put up more such videos, and I'm also going to put up very shortly the concept-based videos in AS A Level and the IGCSE. I'm also going to work on the other boards as well in the OCR, Edexcel and the AQA. So hopefully soon we'll have a much more bigger playlist. Thank you very much for watching, and I hope you continue to subscribe. Don't forget to like and mention your comments as you go through this video. Download it, go through it, and revise your concepts again. And always remember, when you prepare for your A-level chemistry, a substantial part of the AS is always tested in the examinations. So if you really want to study properly for A-level chemistry, don't let go of your AS concepts. It has to be revised again. All the very best, and I'll see you again.